Hello everyone, this is Dr. Webb, and in this video we are going to start what's going to be really one of the biggest topics of the entire term, and in fact it's going to take the majority of the rest of the term to work on, which is derivatives. And so in this video we're getting started in with it, and so let's be introduced to the derivative. So really this resolves around an old problem in geometry, which we'll state as this. So given some nice function f of x, we want to find the equation for the line tangent to the graph at some point a comma f of a. So this is some point on the graph where the x value is a and the y value is whatever the function value is there. Now, the Greeks, they were concerned about finding tangents to curves. And there were some curves that they knew how to do this, like they knew how to draw tangent lines to circles, they knew how to do tangent lines to parabolas, but they weren't very sure on how to do this in general. And so this is what we're working on. So here's some nice function. It's nice enough for our purposes, and we've got a nice dot there at a f of a. And so we want to try and draw the line tangent to the graph through this point there. And so by tangent we mean that we want the line that sort of best fits the function right at that point. So it kind of just glances right off. And so that's sort of my freehand drawing of it. There's a much nicer version of it. And what makes this the tangent line? Well, if we zoom in, you will see, so this is zoomed in by close to a factor of 10, you will see that the line just very nicely just glances off the function at that point. And if we zoom in even more, you can see, so this is zoomed in by about another factor of 5 or so, that the line and the function very close in look very close together. And if we zoom in even more by about another factor of 5, it's almost indistinguishable, the tangent line and the function. So this is what we mean by the tangent line. Now, if our line was off by any bit, if the slope was just a little bit more, we would see in this zooming in that things were not right. And so the tangent line is the one line that as far as you zoom in, as much as you want, it's just going to keep looking more and more like the function. Okay, so here's our picture with our function and our tangent line. So the tangent line goes through the point a f of a, so we can use the point slope version of a line. So this is a point slope form of a line. And so we've made it go through the point a f of a by doing x minus a and plus f of a here. So the only thing that we need to figure out is what the right slope is. You know, we've forced it to go through the point. We just need to figure out what the right slope is to match this function. So really the real problem boils down to how can we get this slope? And so let's start off just figuring out how can we figure something that's close. How can we approximate a value for a slope? So just looking at it, it's kind of hard to, just kind of pull out of thin air a slope. Usually the easiest way to figure out slopes is if you have some other point to choose from. And really all we have is the function. And so we're going to have to pick some other point, perhaps on the function, and then think about drawing a line between our point and that other point on the function. Okay, and this line has a special name. This is what's called a secant line. So we will use secant lines to do this. So a secant line, this is a line between 2 points on the graph. We will always use our point that we want the function to go through as one of them, And then for our other point, we will pick some other point a little bit off from A. And so we can start off, say, picking this point right here. It's a little bit to the right of A. So that's our x value for our other point. And then if we draw a line through there, you can see it's not perfect, but it's actually not bad. It's actually decently close to the line, to our tangent line. What if we want to make this approximation a little bit better? So we want a little bit over to the right. How can we make it closer? Well, we can make it closer if we pick our x value for that other point to be a little bit closer to A. So let's pick a closer value to A. Now let's draw the line through there. And as you can see here, you're just looking as we go farther off, this is a bit closer. So as x is getting closer to A, our new x right here, our slope is getting better. And so if we pick something very close to A, so this is a lot closer to A, draw the line through there, now this is very, very close. And we don't always have to pick points that are to the right of A. We can just as well pick points to the left of A. So here's a very close point to the left of A. And when we draw the secant line through there, again, we can see that it's very, very close. So our tangent slope is going to be close to the slope of a secant line between AF of A and some point x f of x. So how can we write that mathematically? Well, our slope m, well, it's close to the slope between these two lines, or between these 2 points. So how do you find the slope between 2 points? Well, we use the slope formula, right? And so in the slope formula, we're kind of treating A, f of A, this is being x1, y1, and x f of x, that's x2, y2. And so what we end up with is y2 minus y1 over x2 minus x1. And plugging in our coordinates there, we have f of x minus f of a divided by x minus a. Now, as we saw in the picture, as x gets closer and closer to a, our approximation is going to get better and better. So closer and closer getting to a, the slope, our approximation for the slope gets closer and closer to m. What does that sound like we're doing? If we want to get m exactly, we want to kind of think about having x get as close to a as possible, but we can't just set x equal to a in this equation, because then we'd be dividing by 0, and that wouldn't make any sense, right? So what can we use instead? Well, we're going to use a limit. So what our slope is going to end up being is taking the limit of this secant slope. So this right here is representing a secant slope. And then take that limit as the 2 points come together, or as the x value converges onto a. So our m here, so this is our tangent slope. It is equal to a limit of secant slopes. Okay, so let's do this with a tangible example. Let's have the function f of x equals x squared, so we have a nice parabola, and our a value is going to be 1.5. So that's in our nice blue dot right here. Okay, and so if we pick a point a little bit further along, so I think this is at 1.75, and then draw a line through here, this is the secant line. Secant line between, so this is at 1.5 and 1.5 squared, and 1.75, 1.75 squared. Okay, and so you can see this actually looks like this is already pretty close to what our tangent line should be. Okay, so if we want the slope of the actual tangent line, so this m here is not for the secant slope, but this is for the tangent slope, well, we're going to take this limit of secant slopes, okay, and so we've just written out sort of what we talked about before, but now that we have an actual function and an actual value for a, we can start plugging those in. So first, let's plug in a. We're given that a is 1.5. So everywhere where we see a, we're plugging in 1.5. Now let's use that we know that the function is x squared. And so the top becomes x squared minus 1.5 squared divided by x minus 1.5. And we're taking the limit as x goes to 1.5. Now if you look at this, this is very much the type of limit of a rational function that we've been talking a lot before. So how would we handle this? Well, we can factor the top. It's a difference of squares, so we can factor it as x minus 1.5 and x plus 1.5. And then we're dividing off x minus 1.5. Now we have the x minus 1.5 divided by x minus 1.5. And since we're taking the limit as we go to 1.5, we're never actually plugging in 1.5. And so we can cancel these off, and we're left taking just the limit of x plus 1.5. That's a continuous function now, so we can just plug 1.5 in. So the value of this limit is going to be just 1.5 plus 1.5. So here we have 1.5 plus 1.5, and so we get that our slope is 3. So this 3 represents, this is the slope of the line tangent at 1.5, 1.5 squared. Okay. And then we can draw that in. So that is the line. And so in fact, the equation for it, we just plugged in our m into here, and then we're forcing it to go through 1.5 and 1.5 squared by using the point slope form of the line. Okay, and as you can see here, our guess was good, was not perfect. The green line is the perfect tangent line here. So, what does this have to do with the derivative? Well, the derivative is this slope. So given a function f of x, the derivative of f of x at x equals a, denoted f prime of a, is defined as f prime of a is taking this limit of secant slopes. So again, this right here, this is coming from slope formula of a secant line, and we're taking the limit as x goes to a. So f prime of a is the limit of the secant slopes as x goes to a. F prime of a is going to be the slope of the line tangent to the graph at a f of a. In fact, from this we can then spit out what the equation for the tangent line is going to be. In general, the equation of the tangent line, we'll call it t of x, is going to be our slope, f prime of a, times x minus a plus f of a. So remember here, x here, this is our variable. A here is some fixed value that we're plugging in. So a is a fixed value, x, this is our variable. That is all for this video, but we will be talking a whole lot more about derivatives for quite a while, so I will see you again soon.